we're going to start talking about definite integrals. Okay, so in the previous section, 5.1, we talked about Riemann sums and how we can approximate the area underneath the curve using some rectangles of equal length. Okay, so now what we're going to do is we're going to write a definition. Okay, it's going to be the definition of a definite integral. Let me go ahead and let's read the definition, and then I'll draw you a picture of what this is saying, even though we've already seen this picture before. It says f is a function defined on an interval a to b. We divide the interval a to b into n subintervals of equal width, so that means delta x is equal to b minus a over n. And we let x1 equal a, then there's x2, x3, x so on and so on and so on, all the way to your last point, x sub n, which is equal to b. Be the endpoints of the subintervals. And we let x1 star, x2 star, all the way up to xn star be any sample points in these subintervals. So xi star lies in the ith subinterval, xi minus 1 to xi. Then the definite integral of f from a to b is, so integral from a to b of f of x is equal to, oh, I forgot the dx. dx is equal to the limit as n goes to infinity of the sum of I is equal to 1 to n of f of xi star times delta x. Okay? So what we are saying here is we're giving the definite integral a definition. Here's the symbol for it. It's saying the integral, that's what this, it's like a stretched out S integral sign from A to B. This is the lower limit. These are called limits of integration. So this is the lower limit of integration. This right here is the upper limit of integration. And all it's saying is, where are you integrating from? From what x value to the other x value, okay? So, now this symbol right here means the integral, but it has a name as well, integrand. It's called the integrand. Here's the function inside the integrand. And this dx right here acts as our little distance. Remember when we were making rectangles, we had a width, okay? The width of the rectangle was always the same. And this was the height. So all this right here is the heights of the rectangle multiplied by the widths. These are the areas of the rectangle. What this integral is doing, it means a sum. The integral is a sum, an infinite sum, okay? An infinite sum of these rectangles from A to B. And that's what this is saying over here. Remember what we did when we did those Riemann sums. We added up all of the areas of our rectangle, okay? Now, if we read the definition one more time, there's a very important part. It says, let x1 star, x2 star, and so on, xi star be any sample points in the subinterval, okay? Let me go ahead and draw you a picture of what we're talking about. So I just have some generic function, whatever it may be, and I'm starting here at A, and I'm going here to B. I want to find the area underneath this curve, but inside of here. So what I do is I break up my subintervals. So this is x1, x2, x3, so on, so on. This is xn minus 1, and b is equal to x sub n, okay? x1 is a, the starting point of our interval. xn is b, the end point, our ending point of our interval. So if I were to make a rectangle, so it doesn't matter how we make these rectangles. Right now, this is using a right endpoint approximation. But what this is saying is, if you have some interval, when we did Riemann sums in the last section, we did a right endpoint approximation, we did a left endpoint approximation, and we did the midpoint approximation on this interval, okay? A left, a right, and the midpoint. What this definition is saying is that on this interval between the xi minus 1 and the xi interval, so any interval, I just pick a rectangle. If I pick some number, xi star, inside that interval, this xi star could be the right endpoint of the interval, it could be the left endpoint of the interval, or it could be the midpoint of this interval. It could be any point we want on this interval. That's going to become a very important fact in the next section, okay? Any point we want. So, we pick any point, we find the heights, we add up all our rectangles. That is the definition of the integral, okay? So when you, just like when you heard or think of derivative, you should think of slope. When you hear integral, you should be thinking of an area or an accumulation of something, okay? The integral is a sum. A sum is an accumulation, but is also equal to area, okay? Just like a derivative, it means slope, but it also meant rate of change, okay? So, let's see, there's some important theorems that stem from the definition of a integral. It says, if f is continuous on AB, or f only has a finite number of discontinuities, then f is integral on AB, meaning that the definite integral exists, okay? If you recall the definition of the integral, a to b of f of x dx is equal to, it's a limit. Limit is n goes to infinity of the sum I equals 1 to n f xi star delta x, okay? You see it's a limit. So this limit must exist. Not only that, for any choice of our sample points, we should get the same result, okay? So if a function f is continuous, okay, continuous between any a and b, I could dice this area up into rectangles and find the area, okay? So if we have a continuous function, then we know it must be integrable. Now the second case is if it has a finite amount of discontinuities, jump discontinuities. So for instance, if I had a function like this, open hole here, close hole here, and it went like that, and I was finding the area A to B, so I'd want all of that area right there. What you would do is you would cut the graph right along this discontinuity for some C value between here and here. You'd find the area of this first piece, you'd find the area of the second piece, and then you would add the areas together to get the area of the whole piece, okay? The discontinuities don't really cause a problem here. You would just have to break your interval up based on your discontinuities, okay? And it's only a finite number of discontinuities, okay? Of jump discontinuities. There is an example of a function that has an infinite number of jump discontinuities. Now, we cannot integrate this one. It's f of x is equal to 1 if x is rational, 0 if x is irrational. So what this looks like, see, if this was 0 to 1, at 1/2, I'd be at 1, there'd be a dot. Let's see, at 3/4, there'd be a dot up here. At every single spot, there is a rational number, there'd be a dot, okay? So now if I look at a number like root 2 divided by 2, root 2 over 2 is approximately 0.707, but it's an irrational number. 0.707 is about right here. This is 0.75, so it'd be right here. Now, if you were to go ahead and do that for every rational and irrational numbers, you're going to get a bunch of points that sit here and jump up and down. Like that. It has an infinite number of jump discontinuities. So, if we were to try to think of trying to integrate this by finding rectangles and doing areas, well, let me go ahead and find this rectangle. Well, if the next point to it jumps down, and it jumps down, then the width of this rectangle is 0. So then the area of this rectangle is 0. So if I were to find the area from any point to any point, I'd just be adding a bunch of zeros. Okay? So this has an infinite number of jump discontinuities. If you have a finite number of jump discontinuities, then what you can do is split up your interval where those jump discontinuities occur, and then find the area of each piece, and then add the areas together. Alright, let's talk about one more theorem before we do some examples. It says, if f is integrable on a to b, then the integral is equal to the sum. N goes to infinity of the sum I equals 1 to n f of xi delta x, where delta x is equal to b minus a over n, and let's see, xi is equal to a plus I delta x. Alright, so what this theorem is saying is that what you can do is, if you have an integral, okay, you could rewrite it as a sum and calculate the sum this way. Now, delta x, b minus a over n, that didn't change here. This is probably the new part right here. So what this part is saying is that if I'm starting somewhere at a, and let's say here's my function, then to get this next point right here, remember x1 is equal to a. So to get x2, this is a plus, I should be starting at 0 right there. Because if I plug 0 into here, delta x goes away, but that would be x0. Oh, let's see. X1 right there. How do I have it? I do have it starting at 1. So let's make that x0, not x1, because that'd be delta x. There we go. Okay, so x0 is a, so x1, all I do is plug 1 into here. Okay? If I plug 1 into here, you get a plus delta x. Delta x is the width of the rectangles. So to get the next one, x2, that's just a plus 2 delta x. A plus 3 delta x, a plus 4 delta x, that keeps getting you to the next spot in the rectangle, okay? Now, by doing it in this procedure, if you look, we start out with there we go. We start out with I equals 1. So we start out with x1. x1, if I were to look at this right here and right here, this rectangle, x1 is the right endpoint. So what this is saying is that if you have the integral, you could always rewrite the integral as a sum of a right endpoint approximation. Okay? You could write a similar definition to where it's a left endpoint approximation, but we're going to use this fact in the next section to prove something essential to calculus called the fundamental theorem of calculus. Okay?